So the final will be on December 16th, which is on Wednesday, from 3:30 to 5:30 p.m., and that will be through Pearson's My Econ Lab. It will be in structure similar to the midterms, but it will have more questions than the midterm. So this is the information about the final.
Professor, do you think we will have enough time to finish 36 questions in 2 hours?
Yeah, that's something I want to mention right now because I've been approached by some of you that that you think your concern is the time, whether time will be enough or not. And I
Yeah.
think time should be enough, but I'm still thinking about excluding two analytical questions. But I cannot guarantee it for now. Why? Because you guys did really well in the second midterm, and
Professor, for example, for the second midterm, I prepared really well, and I feel like I took all the time you gave us to finish 18 questions, and I wanted to ask, so if these 36 questions will not contain multiple questions inside of each of them, then it would not be a problem. But if, like in the midterms, one question would include like 5 or 3 other questions, that would be a problem.
I think you have a very good point. But the midterm also had questions that have quite a few sub questions. So, and also I have experience of giving exams, giving the finals, and I was always giving 32 questions. But since you did really so well in the midterm, then I thought maybe I could slightly make it slightly difficult, because the thing is that um, I'm fine. So if you do well, you do well. That's perfect, and I'm very happy. But I'm not carving downwards. Do you see what I mean? So I have to somehow construct an exam that will naturally have B minus on average, right? So which was the case for the first midterm, but for the second midterm we had a very high, almost 90 was the average. So that's perfect. But I thought maybe I could put into the exam some more questions that I don't know, but I'm thinking about it. So I will probably exclude two analytical questions, but for now, I would recommend you guys to just try your best, try to do the homeworks, go over the class exercises I've already solved, and I will solve today and on Wednesday. And then also remember that I carve. So just do your best, and know that I will carve, right?
Professor, I just have one thing to add. I think the content itself is fine, right? For us studying and preparing, right? You prepared us well. I think it's just really a matter of time, in the sense that in the midterm too, we had an hour and a half to do 18 questions, and now it's double that, and we only have an extra 30 minutes. So I really just think it'll come down to having enough time. So like cutting questions, I think will be the best thing for everyone, only in the sense that we'll have enough time to actually finish, right?
Yeah, I will think about it. I will think about it, and I think I cannot cut too much, but I am thinking about excluding two questions from the analytical exercises in the final.
Or at least like make it like even like midterm one, because this still ends up being double the amount of what we had for midterm one, and in midterm one we had an hour and 15 minutes either way.
Okay, so guys, for the last time I had uh, I think 30 questions, and 9 or 8 analytical. I'm not quite sure, but there was something like that. And so this time I increased the number of questions, but that was because I think you guys are pretty doing really well. But again, I am thinking about excluding two analytical questions, and I think I will, since all of you think time will be the issue, I will exclude 2 analytical questions. You'll have only 10 analytical questions and 24 multiple choice. Okay, so then just try your best, do the homeworks. And also, the exam is only on chapter 6, 7, and 8. Only 3 chapters. Okay, so guys, let me start today's class. We will do exercises from chapter 8 and chapter 7. Let's start from chapter 8 because it's the most recent chapter that we cover. And see how much we do. Oh, well, no. Yeah, I want to go to person effects. Okay, so this is here. Chapter 8. Let me start by 8.2. 8.2, I think, is about this table. So we have to first copy this table, otherwise we will have to go back and forth. Okay, let me copy this. Paste it here. Okay. Mhm. So when you have this kind of tables, guys, please read the variable descriptions carefully. This is our table. Okay, why? Fine, okay. Now, okay. Now let me copy the question. Copy. Okay. So now I will share the blue screen. And you now see the blue screen, right?
Yes.
So what we have here is that we have a table and this question 8.2, exercise 8.2 is about this table. So here what we have in this table is that we have 5 columns that correspond to 5 different specifications, right? Please note that the dependent variable in these regression specifications is ln of price, the natural logarithm of price. And then we have independent variables that enter the model with levels, for example, size, bedroom, pool, view, those enter in levels. And then also we have certain variables that enter in logarithms, ln of size, for example. And also we have an interaction term, pool times view, that's an interaction term. Also, we need to make a note here that some of these variables are independent variables are continuous, some of them are dummy variables. So this pool view, those are dummy variables. Pool stands for a pool takes value 1 when a house has a pool, and 0 when a house doesn't have a pool. View is another dummy variable that takes value 1 if a house has a view, and it takes value 0 if a house does not have a view. Now the first question, using the results in column 1, so need to be careful, this is about column 1. What is the expected change in price of building a 500 square foot addition to a house? Construct 95% confidence interval for the percentage change in price. Okay, so let's do this. And remember, we are in regression 1. Okay, so this is 8.2 part A. So what are the, let me change the color, maybe it will be better. I will take this color. So what do we have? We have size, right? Size, ln of size to the second power, bedrooms and others, right? But this specification, column 1, includes size and does not include ln of size squared. So we only care about this right now. So, and this is this model is what kind of model? Do you remember? I talked about log linear, linear log, log models. So this model will be linear log, right? Log linear in size. So why? Because we have price in ln, and we have equals beta 0 plus beta 1 times size and plus stuff, right? So this is log linear in size. So then we need to know what's the interpretation of this beta 1. How do we interpret this beta 1, right? This here is an estimated model. So then we have here beta hat 0 and beta 1, beta hat 0 and beta hat 1, right? So, okay, in our case, beta hat 1 is 0.00042. And do you guys remember how do we interpret this estimated coefficient? That's okay if you don't, but for the exam, please try to remember. So this beta 1 is interpreted like this. When size increases by 1, and then we need to make sure what is the unit of measurement of size, and this measured in, let me see, because we need to know that size is measured in square feet. So you see here. Okay, then by 1 square foot, then price goes up by what? Can you tell me? 100 times beta 1 hit percent. That's how we interpret beta 1 hit when the model is log linear. But the question is not about what happens when size increases by 1 square foot. It's about what happens to the house price when size increases by 500 square foot. So then this here is what happens when size increases by 1 square foot. So then, but then, therefore, you can write, therefore, when size increases by 500 square foot, then house price will go up by what, guys? Can you tell me? 500 times 100 times beta hit 1%, right? And then we just plug in the numbers because we know that beta 1 is 0.00042. So the answer to this part A, will be 500 times 100 times beta 1 hit, which is 0.00042. And that is, of course, this is in percent. And the answer here is 21%. Okay, guys, that's how we do it. Now, the next question here is, what is the 95% confidence interval for this change, for this percent change? The thing is that, okay, so guys, are you following? Are you with me? Because I need you to.
Yes.
Yeah.
Yeah, Professor.
Thank you very much. So guys, let me then ask you this very simple question, but we need to still think about it. So when we construct a confidence interval, right? So what do we need for that? We definitely need estimated standard deviation, right?
You need the standard error and the alpha.
Alpha or beta, right? So that's very good, but please also say the estimated standard error or estimated standard deviation, right? Because we never have the true ones, okay? So now we are asked to construct 95% confidence interval for this change, for this percent change. For this, we need to have estimated standard deviation for this percentage change. Guys, do you agree with me? Otherwise, how can you construct 95% confidence interval? But there is something that you can do here. And let's see what it is. Does this work? I think that's fine. We still see what is going on there. Okay, so what we could do is that we could construct 95% confidence interval for beta 1 using beta 1 hat, and then you just multiply that by 500 and then by 100. Okay, then first construct 95% confidence interval for beta 1 using beta 1 hit. Okay, that's easy because that's what, guys? Beta 1 is estimated beta 1 or beta 1 hat is this, right? 0.00042 plus or minus 1.96 because the sample size is large enough here, times, large enough, I mean more than 120, times the estimated standard deviation of what? Can you tell me? Guys, please be involved, and then we will proceed at a good pace because otherwise we have quite a few problems to do today. So times what?
Is it a beta 1 hat as well?
Standard deviation of the beta 1 hat as well, which is in this case what, guys?
1 or 2.
That's the estimated standard deviation of beta 1 hat, right? 0.0000038. Okay, very good. But then this is the confidence in 95% confidence interval for beta 1. But you need to construct 95% confidence interval for 500 times 100 times beta 1, and then you know that this is in percent, right? Okay, that's good. But then if you have 95% confidence interval for beta 1, which you calculate using beta 1 hat, you can just multiply that by 500, 100, and that's it. So the answer here will be 500 times 100 times, and whatever we have here. And you know, this is in measured in percent. So eventually, guys, you will have this 17.276% and 24.724%. That's what you get. So, guys, am I clear?
Yes.
Very good. So that's part A of this question. Now let's do part B of this question. Comparing columns 1 and 2, is it better to use size or ln of size to explain house prices? Okay, so if as you see, column 1 here, this, where is it? Column 1 includes size. Column 2 includes ln of size. And they say, which is better? Should I have size in the model? Or should I have ln of size in the model? If the dependent variables are the same, right? And in this case, all of these 5 specifications have the same dependent variable, ln of price. And remember, if the dependent variables are the same, then you can compare the fit of the regression specifications, the fit of the regression specification using adjusted R-square. And the higher adjusted R-square will indicate better fit. So as you see, adjusted R-square for the first specification is 0.72, which is slightly less than what than the adjusted R square for the second specification. So that probably indicates that it is better to use ln of size as an independent variable in the model. Now let's do part C of this problem. So part B here will be answer will be ln of size, cause why? Because specification 2 has higher adjusted R squared, right? So we denoted by R bar squared, right? Part C of this question. Using column 2, what is the estimated effect of a pool on price? Okay. And then they are asking us to construct 95% confidence interval for that. Specification 2. Okay, so then here is our pool. That's the estimated coefficient that stands in front of pool. That's the estimated standard deviation of the pool coefficient. And this is very similar, guys, to part A of this question, right? The effect of having a pool will be what? So let's say there's no pool. Let's say house does not have a pool. And now let's build a pool, and the question is based on our estimation results, how would the house price change? It would increase by 100 times 0.071%. That's the answer. Part C. And then this is 71, guys, don't get confused. And then I need to construct 95% confidence interval for this whole change, but I cannot do it because I don't have the estimated standard deviation for this whole change, but I do have the estimated standard deviation of this. This is better a pool head, right? But that's okay, right? So can you construct 95% confidence interval for beta pool? Yes. I should have right 95% confidence interval. How? You can use this beta pool head, right? So they will be then, so 95% confidence interval then will be what? You can, guys, please feel free to help me. Plus or minus 1.96 times what?
0.034.
Right? And then, but that's not it, right? So because this is the 95% confidence interval for what? Beta of pool. We want to construct 95% confidence interval for what, guys? For 100 times beta pool. You need the 95% confidence interval for this, right? But if you have 95% confidence interval for beta pool, which is here, we just multiply this by 100, and that's it. So then it is 100 times parentheses 0.071 plus 1.96 times 0.034, and then this, is in percent, right? So eventually you'll have these answers. 0.436% and 13.764%. Guys, am I clear?
Yes.
Thank you. So if you have any questions, please let me know. This is part C of this question, guys. Now let's do part D of this question. Okay, this is just, I didn't look right. I thought I would do it below, but this is part C. And now I will go down part D. The regression in column 3 adds the number of bedrooms to the model. How large is the estimated effect of an additional bedroom? Is the effect statistically significant? Why do you think the estimated effect is so small? Bedrooms. Now we are in this third column. Sorry, guys. I had a mouse that was wireless and was connected to my laptop with Bluetooth. So it stopped working, and now I am suffering, like, because I have to use this. I have a wireless mouse, but not Bluetooth. And don't worry, that's fine. But I was doing this better before because I had this Bluetooth mouse. I have to buy new. That's fine. Okay. So now I can column 3. Okay. So we have these bedrooms here. That's the, what is that? That's beta head of bedroom. I can call it like that. Right. And then we have the estimated standard error. So that's, what is it, guys? It's like the sigma head of beta head bedroom, right? These two heads. Now, two heads. That's important. Okay. So what would be, how do we interpret what happens to the house price when you add one more bedroom to the house? I think now you should be able to answer this question after I have done a few of these guys. It will be like 100, right? Times 0.0036. Percent. House price will go up by Z. This is part D of this question, right? Okay, then what if I added 2 bedrooms? How would you answer that question? So what if I added 2 bedrooms? What would, according to the estimation, our estimation, what would happen to the house price?
Will increase by 2 times 100 times by 0.03.
Exactly, percent, right? That's percent. That's how we interpret the coefficient when we have log linear model. Good. Is this effect statistically significant? Or, I mean, how can you test? You cannot test it, but you can test the significance of this 0.0036, right? How can you test the significance of that? You can use estimated standard deviation of that, right? So and then 0.0036 divided by 0.037. That will be what, guys? Test statistic, right? Which equals to, let me look at my calculations. And this test statistic is really small, guys, right? So is it significant? So this is smaller than even 1.649.
Yes.
Hi. Yeah. So then, I mean, it is not significant at even what level? 10%, right? Significance level, right? Yeah, that's it. Good. Now let's do part E of this. What am I doing here? Part E of this. Is the quadratic term ln of size squared important? Okay, guys, so I do not like this kind of question. When you are asked, is it important? This, like, the answer here is entirely based on whether the effect is significant or not. That's not good because the result can be significant in statistical terms, but can be very small. And if I am telling, let's say if I tell you that, let's say if you, let's say if I'm telling, let's say if you take this, let's say boot camp, and if I'm saying that I am 99% confident that you will say you will score like 0.0001 point higher in some test if you take that boot camp, that would mean nothing to you because I mean, yeah, even though I'm 95% 99% confident and it's significant, the effect is really small. So that's what I'm saying. So it's not about only significance. This textbook equalizes importance to the significance, which I don't think is good. Is the quadratic term ln of size very important? Let me erase it because they just talk about significance. And you know how to test it, right? You just calculate T stat. Which specification was that? This one, right? T stat will be here, what, guys? Here should I write? It will be like this divided by that. And it is 0.55. So it is not statistically significant, guys. Let me do it down. So this is part C, part B, part C. We did above. Part B also we did above. Or E, T stat equals Guys, can I ask you this question? If okay, so we have this situation where the coefficient in front of the ln of psi square is not statistically significant at 10% level. Will it be significant at 5%?
No.
No. Will it be significant at 1%?
No.
Exactly.
No.
Very good.
So, sorry, I do have a question here. I mean, I know that this 0.05 is really small, and like at whichever one we test, it would be way smaller. But generally, when we do this, do you suggest that we do for 10% significance level?
Sorry, can you please repeat? I'm sorry, I could not hear well.
Sorry, when we do this, and I know that 0.05 is very small, and like compared to 10, 5, or 1%, it will still be way smaller. But still, for the testing purposes, do we always compare it to 10% significance level?
No, this question is actually about 5%. I just said that this is like even insignificant at even 10%. But this question specifies tested by 5% significance level.
Oh, okay. But let's say in case it doesn't specify.
Yeah, then
what's the safest bet to go?
I mean, the thing is then, I mean, in this case, it doesn't really matter if the test statistic is really small, but let's say you have test statistic, which is, let's say, it's 1.78. Then what would you do? Right? If the test statistic is 1.78, then this is greater than 1.64 and 5, so that's significant at 10%, but less than anything. I mean, less than 1.96, for example, right? So if your test statistic is 1.78, I'm saying, for example, then you would conclude that the effect is significant at 10%, but not significant or insignificant at 5%. Everything depends on the question. That would be my answer.
Makes sense. Thank you.
Yeah. Or 1%. Good, guys. You're doing quite well. Let's do part A. Now use the regression in column 5 and compute the expected change in price when a pool is added to a house that does not have a view, and then you repeat this for a house that has a view. Is there a large difference is the difference statistically significant? So what this question, guys, is asking is this: if I can articulate it as, let me try to articulate this as much as I can. So there's a house that does not have pool and does not have view. And then suddenly there is a pool. They add a pool to a house that does not have view. Okay, then what happens here? So they want us to see how the house price changes when pool is added to a house that does not have a view. And then there's another situation that there's no pool, but house does have a view. But then they add pool to a house that has a view. So they want us to see the effect here. They want us to see the effect in house prices here, and then they want us to see the change in this effect, right? That's what they want to see. So this is like a beginning point. So we will say that this is a starting point. So this is the effect is 0 because that's the starting point. But now there's no view, but there's a pool, right? Remember, pool and view both are dummy variables. Let's now go up. Look, guys, there's no view, so here will be 0, right? So there's no views, there will be 0 times 0.027 because there's no view. View takes value 0. Okay, then if view takes value 0, then this interaction term also will be 0, right? So the effect will only be determined entirely by pool. And the effect will be what? Can you guys help me now?
0.0.
100 times, right? 100 times.
Yeah, 100 times. 100.
Yeah, 100 times 0.071%. That's good. Okay, good. Now, so the change here will be what? 100 times 0.071%, right? So this is in percent, right? I just subtracted 0 from this, and 0 doesn't change anything, so we are like this, right? Now, there is a view, but there's no pool. So the effect on house price is entirely determined by the variable view, dummy variable view. Do you guys agree with me? Let's go up and then see. There's no pool. There's no pool. So here we have 0 times that. There is view. So, but there's no pool. So also this is 0. So there is view. So the effect will be what? 0.100 times 0.027% on the house price, right? What was it? 0.027? Yes.
Yeah.
Very good. So, but now we have both. We have both pool and view, right? So then we have ones for all these 3 places, right? Specifically, I mean, here you have 1 because house has a pool. So this effect, that coefficient will play a role. There is view, so that means view takes value 1, so that coefficient will also play a role. And then because there is 1, here is 1, then the interaction also will take value 1, so that coefficient will also play a role. Can you tell me then what will be the effect?
100 times 0.0022%.
Not only. So when you have when a house has a pool and also has a view, then these 2 coefficients also play a role in addition to this. So it will be 100 times 0.071 plus 100 times 0.027 plus 100 times 0.0022%, right? So that will be, and you can factor 100 out, so that will be 100 times 0.071 plus 0.027 plus 0.00020. Oh, I think I have extra zero here. And this is in percent, right? Okay, and then what will be the difference here? What will be the effect here? What will be how the house price will change when you add a pool to the house that has a view? So you just take a difference, so you just subtract this from this. And if you do it, what we get is 100 times 0.071 plus 0.027 plus 0.022 minus 0.027. And that's then this will cancel out, right? That will be the effect, right? So here we have 700 times 0.071 plus 0.0022, which is 0%. But the question is not about this. Now you have to use this one and also what we had above this one, right? What am I doing? So this one, right? And you need to take a difference between, you have to subtract this from that. And if you do it, you see that both of them have this. So the effect will be only, so if you subtract that from this, then the effect will be 0.0, sorry, no, 100 times 0.0022%. And then, is this significant? How can we say that? We don't know the standard deviation, estimate standard deviation of the whole thing, but we do know the estimate standard deviation of this 0.0022, more precisely the estimated coefficient, right? And is it significant? You just go up and see that this is the estimated standard deviation of that. 0.0022 divided by 0.10, this is, I think this is big. It's not big, it's very small actually. 0.022, and that is less than even 1.645, and it's clearly not significant at 10%. Therefore, it's not significant at any other conventional levels of significance, specifically 5% or 1%. That's all about this problem, guys. It's quite a large problem. This is quite a long problem, but when you know how to do this, I mean, if we are fair, this can be done in like 5 minutes, because that doesn't take a lot of time. It took a lot of time because I was explaining, but you can do this in 5 maximum. Like 10 is like really much, too much for this. What do you guys say?
It's reasonable.
Question about this. I'm sorry. Can you stay on the regression results? I'm sorry.
Sure.
Sorry for scrolling, but I'm having a little bit of a hard time understanding why do we also use the 0.022? Does that mean that like if house has both pool and the view, that the value added is more than just what pool and view add by themselves? It almost feels like we're accounting for more than that. Like what's the 0.022?
Yeah, so see, that's a very good question, and that's maybe a little hard to understand, but that's what I try to explain here. So see, look at this. So we have a situation where this is, you can say this is situation 1, situation 2, situation 3, situation 4. But you can also aggregate this. You can say that this is situation 1, this is situation 2, but in this situation, there's no view and there's view, right? So what we are doing here is the following. So there's a house that does not have a view and they add a pool. But there's also a house that does have a view, but they add a pool. So the question is, in which of the cases will house prices be, what will be the effect on the house prices when pool is added? What, to be more precise, what will be the change in the house prices when we compare a house that does not have a view and you add a pool, and the house that does have a view and the weather pool. Right? Let me repeat. So
it makes sense. Yeah, that's why the first one is like 0. Now I understand why you did the calculation where you subtract.
Yeah, first you need to calculate how the house price changes for the house that does not have a view, but it's a pool, right? And then you have to calculate the change in the house price for the house that has a view and it's a pool. It's like the effect of adding a pool to a house that does not have a view and a house that has a view. And then finally, you want to see what is a change in the house price when a pool is added to the house that does not have a view as compared with the situation when a pool is added to a house that has a view. So please think about this. You can also listen to this class recording later and think about it. And if you have more questions, you are very welcome to ask. But for now, let me go on because we have a few problems to solve. Now I will, okay. The next, guys, I also want to emphasize that whatever I am solving, the solutions are already on the CUNY Blackboard, and you can take a look at it. Now I will do problem number 8.7.
Professor, do you post the solutions only for the problems that we solved in class or for all of the after chapter problems?
For those who are what I solved in class, yes.
Oh, okay. Thank you.
Mhm. I will have, guys, I am not sure why, but you don't really use, I mean, some of you do attend my office hours, but I mean, not a lot of you. I don't see a lot of you in the office hours. So I'm just saying that if you have questions, you can also ask your questions during the office hours. So, having said that, I want to just emphasize that, okay, so on Wednesday, I will still be solving problems and I will have office hour before class. Okay, guys? And I'm also thinking about having office hour on Friday. So if you have questions, please feel free to attend. I also know you're very busy because you have other classes, not only this class. So if you have time, you are very welcome to attend. So here, guys, do you see the model is again log linear? I would give you like more questions in practice, but okay, we are somewhat limited in time, but still. So the interpretation of the coefficients will be same because I mean it will be 100 times beta hat 1%. Why? Because it's a log linear model. Okay, guys. The question. But should I say this? But what if it was linear log model? What would be the interpretation of beta 1 hat? Sorry, beta 1 based on beta 1 hat. It would be beta 1 hat over or divided by 100 units of the dependent variable. So think about this, guys. Take a look at my notes I posted last time. Let female be an indicator variable. Indicator variable, guys, is the same as dummy variable. So there's like few names. I don't know why we need these few names for the same thing, but we have these few names. Indicator variable, those are the same things. Okay, so female is a dummy variable that takes value 1 if the person is female and 0 if the person is male. And we have these results, and we have SER as well. The estimated coefficient of the female is 0. minus 0.44. Explain what this means. This means what, guys? How can you tell me? How can you explain this? According to this model, can you help me? According to the estimation results, females, on average, earn what? Can you tell? Okay, I always was doing like this. Percent less than math. So this is 44% less. Guys, are you with me?
Yes.
Good. So next, that's what this model tells us. Then the next one is this. The SER is 2.65. Explain what this value means. What is this SER? Do you guys remember what SER is?
It's the measure of fit around the line, regression line.
Exactly. That's one of the measures, one of the two measures of fit. Actually, one of the three measures of fit that we learned. Do you remember what was the other two?
R squared and a
Exactly. R squared and adjusted R squared. So is higher SER better?
yes.
No. Why is it not better? What is SER? Do you remember?
Oh, yeah. Would it mean that the data is more spread out, I think?
Yeah, so that means what is SER? SER, standard error of the model, and that is what? If you remember the formula, I'm not asking you to remember the exact formula, but it has U hat sum of U hat I squared. U hat I is the residual, right? And we don't want the residuals to be like very high, the sum of the residuals, right? So that's why higher SCR is it indicates worse fit, bad fit. And this is that indicates that the data is spread out, like the data is not close to the fitted line. Or in other words, close to the true line. So in other words, you can say that the fitted line is not close to the true population line. Yeah, so 2.65 means that, I mean, you cannot really say that, just indicates a measure of fit. This value indicates a measure of fit. Is it the good fit? Is it the bad fit? We don't know, because there's no, like, for R squared, we have the thresholds. Do you remember? 0, 1. R squared is between 0, 1. Closer to 1 is good, closer to 0 is bad, but also I said we need to be aware that closer to 1 not always means that the fit is great, right? So because maybe indicating some problems that our model may have. And that's it. And now let's do part 3 of this. Does the regression suggest that female top executives earn less than top male executives? Explain. What can you say about this, guys? Does this regression results suggest that females get less, earn less than males? Yes, the regression does, because we have the estimated coefficient, which is negative, right? But can you say that that this regression shows? I'm not saying. Can you say that this regression output shows discrimination in earnings against females?
Oh,
Why? Because lots of other factors could also be affecting earnings, but we don't really include, meaning we don't really control for those factors. If you control, we don't even control for education, right? We don't control for experience. So lots of other factors that are important in explaining earnings. And if you omit those, then you end up having what? Omitted variable bias. So, and that means the coefficient cannot be interpreted precisely. So you cannot really say anything, right? So you need to control for the variables that you think are important in explaining earnings. And then you can say, based on your estimation results, then you can say whether there's a discrimination or not. Unless you control for the variables that are important for explaining earnings, you cannot say anything about whether the estimation results shows signs of discrimination against females in this particular example. Am I clear, guys?
yes.
Okay, now let's do part B of this. Okay, then this regression have been re-estimated, but they included another independent variable, ln of market value. So guys, now please be careful, because now not only earnings are in ln, natural logarithm, but also market value is in ln. So, and the coefficient is 0.37. So what can you tell me about the effect of market value on earnings? By 1%. That's what. Remember, this is an interpretation of log-log model. .37 tells us that earnings on average, I should have noted here, earnings on average this goes here on average, go up by 0.37%, but market value goes up by 1%. Okay, guys? The last one is, are the coefficient on female, the coefficient on female is now minus 0.27. Why is that? Why does it change? Why did it change from minus 0.44?
Because we added new regressors that were correlated with the female regressor.
That's true. That's just the right answer. But does it show that this model suffers by omitted variable bias?
Yes.
Yeah, because it wouldn't if the coefficient was not dramatically changed when we added market value, ln of market value, right? But it dramatically changed, right? Because it is almost half. Do you see what I mean, guys? When you see that, so because we saw the coefficient in front of female, it's almost half after we control for additional variable market value. No, that indicates that this regression is suffering from the omitted variable bias. So we cannot say anything about whether we have, according to this estimation, signs of discrimination, unless you control for the other factors that are important in explaining earnings. But do you think this also might be suffering from omitted variable bias?
No.
I think yes, because I mean, we don't have education, we don't have many other factors. If you need control for those as well, and then you may see that this coefficient may be slightly reduced, maybe even goes up. Who knows, right? What I'm saying is that you have to control for all the variables or as many variables as you can. Do you guys see what I mean?
Yes.
To be able to make proper inferences. Otherwise, you end up having omitted variable bias. Okay. Now let me close today's class here. Guys, what I will do next Wednesday is that so we did do some problems from chapter 7. I will do like, I have made the notes that I have to do two problems from chapter 7, 7.4, 7.5, but I will also try to do some more problems and answer your questions. Remember, on Wednesday before class, I'll have office hour. I'll post the link on the CUNY Blackboard, Zoom link. I'll create a Zoom link and post on the CUNY Blackboard. Please feel free to join, because if you have any questions, I'll be happy to answer. I will also have office hour on Friday. Regarding the exam, as I said, it makes me very happy that you did very well in the second midterm. I had to make the final slightly more difficult, but there will be nothing that we did not count. So it will not be like, you will manage to do it in time if you practice on the homework questions. And remember, the exam is only on chapters 6, 7, and 8. Again, guys, if you have any concerns or questions, you can always email me, but I also will be happy to see you guys in office hours on Wednesday and Friday. Okay, see you in class on Wednesday, guys. Have a nice day and take care.
Thank you, Professor. See you.
Thank you, Professor. Bye.
Bye.
Good morning.
Professor, I just have a quick question
Sure.
about preparation.
Yeah.
So to prepare for the multiple choice part, would you say that going through the homework multiple choice questions would be the best way?
Yes, it will be the best way to.
Okay. All right. Thank you.
No problem. Okay, guys, bye. Have a nice day.